Hello and welcome to part 3 of the iris classification problem. I'm Adam with Push the Envelope, the channel that gives you everything artificial intelligence and machine learning. Today we're going to be looking at another classifier to solve the iris classification set, and that will be the K nearest neighbors algorithm, or KNN for short. If you haven't heard of this before, I have an example video where we go through exactly how KNN works for beginners and show you some example problems of how we can use it to solve our problem. Also, if you have not seen the beginning of this series, I will be using some of the code that I put together in the first two videos. So go ahead and check those out. I have links to all of this right now, so just click those and swap over there and go ahead and get caught up. But for now, let's swap over to our Jupyter notebook and get started. Okay, pulling our code up, you can see we have what we did the last time. So if you haven't tuned into the first two videos, I again am going to highly recommend you go check those out because we're going to be reusing a lot of the code. What we did was we imported the data set and we scaled it between 0 and 1. And then we split it between training and testing sets. For those who did join in to the first two videos, I have basically just deleted everything that was for the decision classifier. So we're starting right from the point where we split into the training and testing sets. So let's go ahead and get started here. First thing we need to do is import our new model. So that's sklearn.neighbors. We are going to be importing k neighbors classifier. Go ahead and run that, get that in here, and we will go ahead and get started. So now, if you haven't already run this, go ahead, get your training and testing data, and we can start, like we did before, creating a classifier. So CLF, however, in this case, will be equal to the k neighbors classifier. Now, I don't need to pass in the random state here because the KNN algorithm will give me the same results every single time I run it. There is no randomness with this, so I don't have to worry about that. But I will go ahead and do a clf.fit. I'm going to be passing in the training data, so the Y train and the X train, and then I'm going to be scoring on the test data. Same way we did it for the decision tree, but for those who didn't tune in, clf.fit is my train function, so I'm going to be training on X-train data with the Y-train labels. Then I'm going to be scoring based on the test data that we held out. So I'm going to be taking the X values, predicting on them, and comparing them to the Y test values. Go ahead and run that. As you can see, we get an accuracy. I believe this was the same as the decision classifier accuracy. So we're not really improving from there, but this is a really good accuracy. So let's go ahead and see if we may be able to bump this up. And we're going to do the same thing that we did before. We're going to be using the randomized search and the grid search to help us fine tune our hyperparameters and see if we can bump up our accuracy. So first thing is we need to define some parameters we are going to be iterating over. Now, these are going to be different than the decision tree parameters because we're using a different algorithm and it has different hyperparameters that we can fine tune. So first one, most important one, is the number of neighbors that we are going to be predicting against. How many we're going to be using to make our prediction within the KNN model. I'm going to be using a whole bunch of these just to test which one performs best. So I'm going to do np.arrange. I'll do 1 to 15. So I'm going to be looking at neighbors from 1 to 15. Next, I'm going to be seeing how much we want to weight those neighbors and how we want to weight them. So you can either weight them uniformly, so uniform, if I can spell. And other ways, you could do it by distance. So just how much you want to weight each of those neighbors based on how far away they are, if you want to do them all as one. Next one is algorithm. And this is going to help us determine the distance. So we can go ahead and do it based on whatever the auto is. Other ones are ball underscore tree, KD underscore tree, or brute. Okay. Next one is defining the metric for distance. First one is the Minkowski, Kowski. You can do Euclidean. Next one is Manhattan. And next one is Chebyshev. That's ChebyshEV. All right, so 4 distance metrics that we can look at. And the last thing we'll do is the leaf size. And we're going to do a bunch of values for this. So np.linspace. So I want to take values over 10 to 150, and I want 15 of them. So that should be increments of 10. We just put that as 150. And for now, those are the parameters that we will look at. So let's go ahead and define our new model. Call it rand_search. And that is going to be equal to our function randomized search CV. We are going to be passing in our estimator. So that is k neighbors classifier. We are going to be, so that's our estimator. Now we're looking at the parameters that we're going to be testing. So that's the parameters dictionary that we just created. We're going to be scoring those based on the accuracy. And let me just drop this down a line. Now, within randomized search, there is some inherent randomness, so I will be fixing it here. So random_state is equal to 1. And then for cross-validation, we'll say CV is equal to 5. Okay, now let's go ahead and fit our new model. So random search.fit, passing it X train data and the Y train data. Okay, now that we have it fit, let's go ahead and print out some of the results from it. First thing, if you remember, was the parameters. So random_search.best_params. And we're going to actually save this as random params. So we're pulling out what the optimal parameters were found to be and saving into a variable. And let's just go ahead and print that with a divider. This is going to look very similar to what we did for the decision tree. We can also go ahead and print the training accuracy. That is going to be equal to the random search, the model that we just made, dot best score. Next, we can go ahead and use our model to predict on the test data. So I'm going to make a new variable called predictions, and that's going to be equal to the random_search.predict. We're going to be predicting on the X test data. And last thing we're going to do is just print that accuracy. So test accuracy is going to be equal to the accuracy score. This is a function that we imported from sklearn. So the accuracy score pass in the predictions and the Y test. So predicted values and the true values. Let's go ahead and run that. And you can see it gave us the optimal parameters that it found by randomly searching this. The training accuracy actually went down. So it obviously didn't, in this, since I fixed the randomness in this random state, it didn't actually search for the whatever the defaults were. So that is why we actually had a worse test accuracy. But our our test accuracy is actually better than it was up here. So we actually hit 100% with our test points, but our training accuracy is still down 95, 96%. Okay, so let's see if we can maybe improve that a little. Let us go ahead and I'm going to copy everything I did here. Now, I'm going to copy everything I did below the parameters. First, before I do the parameters, like I did before, anything with a number, I want to kind of do some below it and some above it. So the first one is going to be the n neighbors. That is going to be equal to np.arrange. And we're going to be taking random params and that is going to be at the nearest neighbors. So n neighbors, number of neighbors. Again, number of neighbors. So I'm taking this value here. So the value is 7. I want to say what's 3 below that up until 3 above it. I'm actually just going to copy this here. So I'm just checking around what it found to be the optimal solution to see if we can get even better. So that takes care of the number of neighbors. Let's go ahead and do leaf size as well. And that again is going to be equal to np.arrange random params, except for this time it's at leaf size. And I will let's just continue doing 3 above and 3 below. We go ahead and copy this. Okay, now I do need to define parameters. So let me copy this down here. Nearest neighbors, instead of doing all of these values, I just defined my new set of nearest neighbors. Weights, I'm going to take what I learned from up here. So that is going to be rand params at weights. Algorithm, same thing. So rand params at algorithm. One more time for the metric. And lastly, leaf size, which is the variable I just created. So leaf underscore size. So for those who didn't tune in to the first video, what I'm doing here is I'm taking what I learned from the random search, looking at any number value, I'm going up and down a little bit, and everything else I'm keeping the same. So anything with like a string that's set to some metric or some algorithm, I'm keeping the same. Now, let's go ahead and create a new model. Instead of rand search, we are going to call this grid search. And instead of randomized search CV, we are going to be using grid search CV. I'm still using the K9 classifier. We are still looking at the parameters using accuracy. Since I'm using grid search, I do not need to use random state, so I'm going to get rid of that. But everything else stays the same. Now I'm going to be fitting the grid search algorithm with the training data. I'm going to be looking for the parameters for this function that I just created. So let me go ahead and change those. Coming down here, I'm going to print those. Basically everywhere it says rand, I'm just switching to grid. And that should be fine. Okay, so let's go ahead and fit the data and see what results we get. I do have an error going on here. Long error. Okay, looking at the error, it says metric root is not valid. So going up here, I can see that instead of passing in the random parameters at metric, I pass in algorithm. So go ahead, change that, rerun it. And okay, now you can see it didn't really change, but it did find a more optimal leaf size, and the neighbors stayed the same. So the changes aren't apparent here, but like I said, these scores are very good. This is a very well-known data set, and it's fairly easy for beginners because you can get such high accuracy. Now, when you do real problems, while it wasn't super important here, these random searching or grid searching can actually help you out to figure out what's your optimal solution, and you could see some changes in results when using them. And last thing I'll do is, like I did last time, I will print a classification report. And we will use the predictions and the Y test values. And you can just see, obviously not telling us a lot because we scored 100%, so everything is perfect here. But if you didn't, then you would be able to see that there. So that is all for the KNN algorithm. We were able to get higher accuracy on the testing data, but we did get worse training accuracy. So there are some points in there that were confusing for the K and N, but the decision tree picked up, and vice versa. So hope you guys got something out of this. Definitely like the video, and I hope you stay tuned to more series that I put out there. I'm going to be starting to ramp up more examples like this, and once I get past the beginner examples, we'll work into some more real and realistic problems, and should be a lot more exciting than this iris data set. But stay tuned, stay subscribed to the channel, and thanks for joining me.